Welcome back, AP Statistics. This is Chapter 14, Probability Rules. We'll be picking up where we left off in Chapter 13 in our discussion of probability. First, let's talk about events that are not disjoint. In the last chapter, we assumed when computing probability using addition rules that events were disjoint, meaning that two events, say A and B, cannot happen at the same time. Well, we are going to be looking at situations where A and B can happen at the same time, and we need to change our rules of probability a bit. So in Chapter 13, we discussed how events can be disjoint. Another word is mutually exclusive, meaning that events have no outcomes in common. That is, they cannot occur at the same time. We learned the addition rule. Probability of A union B, or we would normally just say A or B, is probability of A plus the probability of B. However, if we wanted to find the probability of two events that were not disjoint, we'll need to change our formula to avoid double counting the outcomes that the two events share. So what happens is, if I'm trying to find the probability of A or B, I would count the ways that A can happen and the ways that B can happen, but if I do that, I double count the ways that A and B would be happening. All right, so if A and B can happen at the same time, I double count those outcomes, and that's going to mess up my probability. I need to do something about that. I could explain this with an example. If we were to find the probability that an FCA teacher is male or teaches math, so whether you're male or teach math, we want to find the probability you fit one or both of those categories. There are several male math teachers, myself included, who would be double counted if we just use the probability formula. Probability of male or math equals probability of male plus probability of math. I and every other male math teacher at FCA would be considered in this probability and in this probability, even though we should only be counted once. So how do we fix this problem? Well, we fix this problem by using a slightly different formula. We use the general addition rule. To accommodate for events that aren't disjoint, we can upgrade our addition rule to make it a general addition rule. And when I say general, I don't mean a general like Douglas MacArthur over here from World War II. I mean general as in it works universally. The probability of A or B equals the probability of A plus the probability of B minus the probability of both. Here's why this works. In this first circle is the set of all events that include A, or that would satisfy A. Here's the set of all the events that would satisfy B. Here's the set of all the events that would satisfy both. If I want to find the probability of A or B, I want this circle and only include the intersection once. If I don't have this last part of the formula where I take away that intersection, I would be counting this intersecting part twice. Then I wouldn't be finding the probability of A or B. I'd be finding the probability of A or B, and oh yeah, we're going to double count everybody in this group right here, but we don't want to do that. So we find the probability of A, that's this circle, the probability of B, this circle, and that part we just included twice, we subtract it out. So now let's use the general addition rule. A survey of college students found 56% live on a campus residence hall, 62% participate in a campus meal program, and 42% do both. The question our textbook asks is, what is the probability that a randomly selected student either lives or eats on campus? And of course we mean lives on campus, not lives altogether. I hope these students are all alive, but I digress. Think about how you would solve this problem and see if your answer agrees with mine. Unpause the video when you think you have the correct answer. All right, I'll assume we're ready to continue. Our textbook gives a good explanation to this problem, And the textbook starts by doing a little bit of abbreviation, but it describes what the abbreviations mean. So the book says, let L be the students who live on campus, and M be a student that has a campus meal plan. So you have L and M, L for living on campus, M for having a campus meal plan. The probability then that a student eats on campus or lives on campus is probability of L union M. Looks like it says plum. Anyway, probability of L plus probability of M would be our old addition rule, but we need to acknowledge that 42% of this college population do both. So we need to make sure we don't double count by subtracting the probability of lives on campus and has a meal plan. So we would say 56% live on campus, 62% participate in the meal program, and 42% do both. So we need to make sure we don't double count that 42%. That would even out to 76% either live on campus or enjoy the campus meal program. Now we're going to find probabilities using a Venn diagram. Venn diagrams are awesome for addition rules situations when events can overlap. We're going to return to our survey of college students. 56% live on campus, 62% have a campus meal program, and 42% do both. Based on the Venn diagram, what is the probability that a randomly selected student A, lives on campus and doesn't have a meal program, and B, lives on the residence hall but doesn't have a meal program? Okay, so I want to just explain this Venn diagram here. We see that 56% live on campus, but 42% also have the meal program. So we take this 42% and we put it in the intersection. That's always how we should start a Venn diagram. Find the both statistic here and put that in the middle of our Venn diagram. Now we think to ourselves, 56% live on campus, but 42% are in the middle. That means the balance, the 14% over here, live on campus but do not participate in the meal program. Similarly, we see that 62% have a campus meal program and 42% also live on campus. That means the balance, 62 minus 42 is 20. 20% of students have a meal program but are not living on campus, right? And then we consider these three probabilities right here. That's not 100%. We have a total of 76%. As we found in the prior problem. So the balance, 24%, neither live on campus nor enjoy the meal program, okay? So that's how we build our Venn diagram, and later on we'll be building our own Venn diagram, so you'll get a lot of experience there. But let's first try to answer these two questions. What are the odds that we live off campus and don't have a meal program? And then what are the odds that we live in a residence hall, that is, we live on campus, but we don't have a meal program? Okay, so give it a go. Unpause the video when you think you have an answer. All right, I'll assume we're ready to continue. Here's the answer for part A. Probability of off-campus and no meal program. That's the probability of not living on campus and not enjoying the meal program, all right? That's going to be 24%. So we don't want to be here, and we don't want to be here, and we definitely don't want to be here. So we want to be in the 24% over there. Now let's go to part B. The probability of on campus, so we're in a residence hall, and no meal program is probability of yes, we want to live on campus, and no, we do not want to enjoy the meal program. So we would say, okay, I want to be in the L category, all right? That would actually be a W to be in the L category, but it would be a problem if we were over here because we don't want to be in the meal program. We just want to live on campus and make our own meals or just eat ramen or something like that, or just survive off of coffee. If you go into engineering, you'll understand what I mean. that would be the 14% right here who are enjoying living on campus but are not partaking in the meal program because their ramen and coffee are just not to be missed, I guess. Now let's do a problem where we need to start by building our own Venn diagram from scratch. You probably qualify as an online adult, an adult who uses the internet. If you're not there, you're quite close. Pew Research tracks the behavior of online adults. In 2016, they found that 79% were Facebook users, 24% used Twitter, and 22% used both. How they got that information, I don't know, and I'm not sure I want to know. For a randomly selected online adult, what is the probability that a person, 1, uses either Facebook or Twitter, 2, uses either Facebook or Twitter, but not both, or 3, doesn't use Facebook or Twitter at all? All right? So, what we're going to do first is we're going to fill in this Venn diagram right here. And we're going to start by defining what the two circles represent. We have Facebook users over here, and we have Twitter users over here. That means that the intersection right here is where people use both Facebook and Twitter, and the blank space right here is where we write the name of everybody who doesn't use it, or rather the percent of people who don't actually use either, and are probably spared a lot of drama in the process. So let's start putting some probabilities in these spaces. We have 22% of people who use both. All right, so 22% use both. That goes here, and we plop that right here first. We also know that 79% were Facebook users, but 22% used both. So in the just Facebook and not Twitter category, you have 57%. Likewise, we have 24% used Twitter in 2016. So we have 24% using Twitter minus the 22 that's in the middle, and this is a mere 2%. Then we consider 57, 22, and 2, that would add up to 81%. So the balance, 19%, use neither Facebook nor Twitter. We now have enough information to solve the problem. Just as a recap, we start by putting the intersection, the probability of being in the intersection of the sets here first. Then we figure out how much of the group we're dealing with go into the categories on the left and the category on the right, but not the category in the middle. And we do a little subtraction in the process. And then we consider how many people fit in neither category, and we stick it in a corner somewhere. So let's see if we can answer questions 1 through 3. Try each of them using the Venn diagram, and then check your answer against mine by unpausing the video. Okay, I'll assume we're ready to continue. Let's look at these answers. We want to find the odds of using either Facebook or Twitter, okay? That's going to be 57% plus 22% plus 2%. All I did was I took each of these spaces and I added everything up. That's going to be 81%. What I also could have done is said, well, I could use the complement too. If I want to find the odds of using either Facebook or Twitter, the complement of that would be using neither. And the odds of using neither would be 19%. 1 minus 19% is 81%. Now let's look at number 2. Uses either Facebook or Twitter, but not both. That's going to be 57% plus 2% equals 59%. I use this partial circle over here, this very tiny partial circle over here, and I don't want to include the overlap because I don't want to use both. And I certainly want to use something, so the 19% is right out as well. Now we want to find the odds of not using Facebook or Twitter, and that should be obvious at this point. It's just 19%.